Salutations, and welcome to our presentation on Industrial Control Systems Security. Our team includes Owen Cummings, Jason Hong, Robert O'Shaughnessy, and Jamie Sinn. What follows is a walkthrough of our Capstone project. Industrial Control Systems, or ICS, a subset of Operation Technology, or OT, encompass systems that are designed and implemented with the goal of interacting with real-world or physical processes. While the term ICS is often generally applied to overlapping domains, such as the Internet of Things, we use this term to refer specifically to industrial control processes, typically those associated with critical infrastructure. Public Safety Canada refers to critical infrastructure as processes, systems, facilities, technologies, networks, assets, and services essential to the health, safety, security, or economic well-being of Canadians, and the effective functioning of government. ICS security differs from traditional IT security. These differences are not just in the processes being secured, but also in the architecture and in the design decisions. The displayed figure shows an example of a notional ICS architecture. Malware used to target ICS contrasts that used against traditional IT systems. Data exfiltration and denial of service attacks are common in classic environments, but attackers often write code that affects physical processes within OT. This is found to be true in the cases of Stuxnet, Trisis, and Black Energy 3. Malfunction of a physical component in a system can be a health and safety concern as well as a monetary one. Therefore, the impact of an attack on ICS often has greater risk connotations. In the operational technology field, security research on live environments is often unsafe and impractical. It was reported in 2005 that a simple ping sweep on an active supervisory control and data acquisition, or SCADA network, resulted in a massive failure at a factory operated by Sandia National Laboratories. The consequence of the sweep was the destruction of 50,000 USD worth of inventory as the scan inadvertently moved a 9-foot-long robotic arm on the shop floor. OT systems such as this are vital to an organization's production capabilities. Any significant amount of downtime due to security testing could lead to catastrophic circumstances. Given what was stated previously about the importance of ICS and how hard it is to test, it follows that an environment must be made to assess the security of operational technology. The solution proposed was to create a testing ground and proof of concept for assessing industrial control system security. The end goal is an environment with a modular and scalable design that would allow various research projects to utilize this space effectively. The project scope includes developing the network security architecture required to test real-world scenarios securely and safely in ICS equipment in both a simulated and physical capacity. The project has been scoped in the two major cooperating goals. The first was to create an environment capable of interacting with real-world ICS. This will allow the simulation of various infrastructure setups for research purposes while reducing the effort required to stand up these environments. The second was an actual proof of concept, POC, that exists and interacts within this environment. This POC would be a demonstration of the ability to set up and interact with an ICS, specifically a programmable logic controller, or PLC, in the designed environment.
The purpose of the cloud infrastructure component is to support research projects within the environment. This involves deploying resources to simulate components of ICS environments and any other supporting infrastructure to make research easier. One of the most important design requirements was creating a way for researchers to deploy pieces of infrastructure quickly and safely. To accomplish this, two main pieces were implemented. A workflow was developed to allow researchers to define and build images that run on VMs in the lab, and a workflow that deploys infrastructure defined with code to our cloud environment. To accomplish our goals, we elected to use a cloud service provider, GCP, also known as Google Cloud Platform. This reduced the overhead of deploying physical systems to support the project and made management easier for us. Here is a notional design for the deployed lab. Supporting infrastructure is deployed in separate networks with specific access to the lab, such as for collecting logs or sniffing network traffic with packet mirroring. The lab network itself contains things like human-machine interfaces, workstations, historians, OPC servers, and any other virtualizable ICS infrastructure. This lab then uses a site-to-site VPN tunnel to connect any resources in the cloud with physical on-premise resources. Here's a quick overview of the tools we used. The code bases for anything we want to put in the lab are hosted on GitHub. This helps track the state of our infrastructure and provide version control for our code. From there, GitHub integrations allow us to set up pipelines to Google Cloud where the code is built and deployed. The most important Google Cloud Platform tools we leveraged are Google Cloud Build, Compute VMs, and the VPN. The two workflows I spoke about earlier are largely executed in Google Cloud Build. Repositories on GitHub contain files that define build pipelines. One is for deploying infrastructure defined in Terraform, and one for VM images defined in Packer, which I'll talk about later. Compute VMs largely host everything that we have in the lab. Depending on their purpose, we attach these to different networks. For example, we can create a network and deploy an elk stack for logging. The deployment for these VMs is also defined in Terraform. The VPN itself is relatively simple, and it just provides connectivity from our cloud network to the on-prem lab. Terraform is a tool from HashiCorp that allows infrastructure to be defined using code. It creates API calls to whatever provider you're using, such as Google Cloud, to tell it exactly how you want to create a given resource. Every time a modification is made with Terraform, it checks the state of all resources it manages and reconciles any changes back to how it's defined in the code. Packer is also from HashiCorp, and it allows for the definition of our VM images with code. You define what you want to base the image off of, then steps to run it to build the image, and then once it's built, it takes a snapshot and ships it to where we can access it from within the lab. Deploying custom VMs to the lab environment is important functionality. Here's an example of what building a security onion image looks like. Let's say you want to configure a security onion image to deploy. Doing this is relatively straightforward with Packer. You define a Packer template using JSON, which calls a different configuration component. In our case, we use a basic builder to give the Google provisioner information like what Google project to put it in, the image we will base it off, and what we want to name it. To configure the image, we'll use some provisioners. The file provisioner lets us drop a config file for security onion into the VM, and then the shell provisioner lets us execute a setup script that we defined. All these changes are made following the usual GitHub workflow of making a new branch, creating the files, then opening a PR which triggers Cloud Build. The setup script we run with Packer is simple. It copies the security onion config to a location we can use, updates all the apps, then runs the security onion install command. Once the script is done, a snapshot is taken of the instance and the image is made available as a VM image in the cloud. For the sake of keeping this organized, I'll talk about the process of deploying the lab for the proof of concept. This can be accomplished with some automation and a few manual steps. First, we write the Terraform calling the desired modules, we push the changes to GitHub on the production branch, and then we watch the Terraform deploy. Once this is done, all we have to do is set up a VPN tunnel from the cloud lab to the network. Modules are a way of calling multiple related Terraform resources with a single block. This makes management much easier. In our case, they define resources needed to deploy a given component of the infrastructure. All we do is call a module block, provide any inputs needed such as network ranges or links to other resources, then the rest is handled by the module. For example, the security onion deployment defines a Google Compute instance which runs the image we built earlier. This module also configures a network to attach this machine to, creates firewall rules to permit traffic we want, and sets up a feature called packet mirroring to send a copy of VM traffic from the lab network to our security onion instance.
The goal of the ICS POC is to simulate a real-world environment with as low cost as possible so we can actually afford making a physical POC, but it's also making sure that it's scalable to allow for future expansion and development by other researchers. We also need to ensure that it's simple enough, but accurate, to pitch to real-world use cases such as experts and industry. To ensure this also is continuous with industry, we have to use the same industry software and hardware and protocols to allow portability for ICS experts and researchers so that we don't have a one-off environment that is not reflective of real life. But most of all, this needs to be accessible. This means you can't be trapped by license costs, versioning hell from software, stupid Java applets, and dumb requirements that other vendors have that CAMDT and Sheridan will not be able to maintain. To do a quick walkthrough of the big names in ICS to get a little bit of context, where you have Siemens and Allen Bradley. These are the two biggest players running a huge amount of the ICS infrastructure in the world. Both are extremely expensive and extremely long-lasting. Installations can be over 20 years old and still running today. Onron is more focused on smart relays and relay technology as a whole, but they do PLCs. Backoff is extremely focused on detailed motion control systems with safety integration as well. The caveat here is big name is equal to big money, meaning we don't really have an option for using any of these people. To avoid this, we have to use a modern system that would also be well supported, and in order to find someone to do this, I turn to one of my previous contacts, Automation Direct. They're a reseller/manufacturer for Koyo, a very well-known Japanese ICS manufacturer that has a great name in the industry. They were more than happy to help us out with sponsoring all of the ICS infrastructure we needed, totaling around $1,200 US, including the PLC, the motor, and the VFD, as well as the wiring solutions we need. If you're thinking of getting into ICS, I would highly recommend looking at their options, as they're very reasonably priced. For a little bit of the design-wise, we have a semi-gold standard of the DEF CON ICS Village. They have a water pumping station that has physical water going around and uses a wide array of PLCs to ensure coverage across the industry. They have a humongous amount of variation points in this. It's much too complex for our uses since we need it to be dynamic and reconfigurable, and we can't have it break because of misuse or lack of use. So let's dumb down the water pumping station. There's a PLC controlling a variable frequency drive, which then controls a AC three-phase motor. This is usually with a local input to start, stop, and change frequency of the motor. Frequency is the speed of any motor in the AC world. There's also likely a remote input method, since there's not someone pushing buttons at every water pumping station around the country anytime the water demand changes. We can expose the VFD directly to Ethernet, since that's how the PLC will be communicating it with over MODBUS TCP or Ethernet IP. This then means we can also expose the PLC directly to the network and have other further access points through that. So let's take a tour through the process it took to wire this thing up and bring it up to what our test and demo setup is. I'm rather qualified with this. It's my hobby, and I have done a little bit of professional work in it too. In the left of the photo, we have the VFD, which is the black box. That is being wired up for the output stage to the motor. On the furthest left, you can see its little yellow cover on the output shaft. In the middle, we have a 120 volt AC to 24 volt DC power supply, which powers the PLC and some I/O for the future expansion. The white brick is the CLICKPLC, which is the brains of the whole setup. The bottom area has terminal blocks on DIN rail, which is an industry standard mounting system, and all of this is going to be used to wire in all of the connections and ensure that we have portability and ease of use for the future. On the right is the buttons in their deconstructed formats, as we have to configure them to be either normally open or normally closed. Later on, we have it a bit more wired. I have it connected up to enough to verify that everything works and everything will be powered properly. There's not great cable management. It's kind of haphazard as there's no actual mounting surface. This is just sitting on the desk. Everything seemed to work happily. We had a little bit of an issue with the PLC that we had to get replaced by Automation Direct, but they're super awesome on their tech support that way. So after everything is wired up, we're good to verify the next step, which is ensuring hardware is ready to go. With the hardware tested out, we have everything we want and are starting out to wire it properly. I designed a layout for everything that would be nice and easy and a bit future-proof with expansion and where we can put things. I designed this in SolidWorks and cut it out of polycarbonate using CAMDT's waterjet, which is basically 80,000 psi water and sand to cut through basically anything and everything at extremely quick speeds. This allowed us to mount the DIN rail and the buttons along with the VFD securely, so that way we can mount this somewhere else in the future, as it will have a permanent home in CAMDT. Further down the line, I have everything wired in, even though it's a little bit semi-messy right now from our testing and our demo recording. Each of the buttons is wired into an input, which then is wired into the terminal block, which is then wired into the PLC. All of this is set up with 2 spare buttons for future use. We have buttons of start, stop, change direction, and change frequency. The VFD is wired and connected to 208 volt AC input, which is what CAMDT has available in the lab, but the VFD technically is tolerant from 200 volts to 260 volts AC. The VFD and PLC are both connected to an unmanaged Ethernet switch, as is somewhat common in industry from my experience. This allows us to have no packet filtering and no direct firewall and access control rules on the Ethernet switch, but a managed Ethernet switch would be much better in terms of security. And this is how it is currently. CAMDT helped us out and made a really cool frame using aluminum extrusion. It looks a lot better and is a lot cleaner looking, just no longer lying flat on a desk and waiting for prodding fingers. We have the variable frequency drive all propped up and it looking nice in the center. The buttons are still there on the top left. We have the VFD underneath the VFD in the white brick. All of this is wired in to that same Ethernet switch, which is then connected to the black box underneath and beside the aluminum extrusion. This is our PFSense appliance that we have configured using the network setup that Sheridan has given us, as well as the IPsec tunnel, which goes into Google Cloud to connect to Owen's ICS cloud setup. We also have a spare router on the furthest left in case we want to simulate further routing environments, such as having a more air-gapped or more security-controlled environment that has physical on-premise hardware or other future expansion. CAMDT also helped us out, and using their really cool, expensive 3D printers, printed us a impeller housing to make it simulate even more of a water pumping station. Hopefully it doesn't blow up when we try and spin it at 4,000 RPM. Now, lastly in the overview, we need to connect all of this to the internet or at least some degree of the internet, as almost all ICS setups are very rarely fully manned. Oil and gas rarely have anyone on site because these are remote situations. Water filtration and pumping rarely have people on site. The gold standard for this is a remote SCADA connection over a secret or private VPN. We are trying to set this up so we can tunnel into the cloud and manage everything from there, but we have two options. We can either have a Sheridan managed demarcation and router, so Sheridan manages the VPN appliance and manages routing configurations, manages security, or a researcher managed, where the researcher can apply routing rules, control the router, and ensure that everything is set up for their environment without having to bug Sheridan. The Sheridan managed DEMARC has a higher initial cost for the researcher, ensuring that the researcher can bug Sheridan and get anything configured for the router, slower turnaround times, more management. But a researcher managed setup has higher portability but lower security, meaning that the researcher is responsible for security. After going back and forth with Sheridan on this and getting their input from Sheridan IT, we decided on researcher managed because they were able to create a VLAN isolated for us and only us, where we have one address and absolutely no access to the rest of the Sheridan network. It's fully DMZ'd as if we were on our own entire internet connection. This way we can manage our own firewall rules and have direct access to the router. This was critical for us because we needed to get packet captures to ensure that the attacks were going through and we were able to see how everything was running. This also allows future researchers to do their own more advanced packet captures or filter controls or inspections. This also allowed us to do a little bit more control and testing because we had a lot of trouble setting up the IPsec tunnel to properly work with routing rules for the Google Cloud setup.
So in addition to other design considerations, we need a way to facilitate communication within industrial environments, and this is typically done via automation protocols, also known as industrial control protocols or ICS protocols or industrial networking protocols. Some examples include MODBUS, Ethernet IP, DNP3. If you Google a list of industrial protocols, you will probably come across dozens of them. Causes of protocol insecurity are generally related to ICS security. In terms of protocols, they're often proprietary or untested. Sometimes they are even relegated to very obscure applications. This is becoming less of a problem these days. I think manufacturers now are, trying to default to common protocols, but because the life cycle of, industrial controlled environments are typically decades, you are still likely to come across, very obscure protocol. In case of proprietary protocols, there's obviously a lack of supported documentation. We have our typical budget, expertise, time constraints, and we also have other design and implementation decisions that we need to consider. So for example, if a device requires 100% uptime and 100% real-time communication, it may not be able to tolerate the overhead of cryptography. We chose MODBUS. MODBUS is a very common automation protocol. It is open source. It is considered a de facto industrial networking protocol, and what that means is that it is very, 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 very common. And there are many implementations of it. We chose MODBUS TCP chiefly for its simplicity, its use of the TCP IP stack. Because of its open source nature, there is a lot of support and libraries available. And from an attacker and demoing point of view, it is very easy to sort of demonstrate and show. So MODBUS is an application layer protocol. And as you can see here, next to the OSI layers and on the TCP IP stack, This is the general structure of a Modbus frame. The main frame is called the ADU, or Application Data Unit, and it contains all the information needed about the packet, including the unit ID or device ID, transaction ID, which is useful for tracking requests and replies, and the actual payload, also known as the PDU. The PDU contains the function code. This is the actual operation that we want, and any relevant data. So the most common functions include, reading from writing to coils, reading from or writing to registers. And because we are utilizing the TCP IP stack, we can rely on our usual IP addresses and host names and port numbers. Modbus defaults to 502 port number. The next two slides here show Modbus in operation. It is a very simple protocol. Client initiates a request. Request contains function code and any associated data. Server attempts to perform the action and then initiates a response. The response contains an exception or error if applicable. And these errors are very useful from an attacker point of view to find legal and illegal addresses or coils or registers, and finding legal and illegal values. So what we did was we created very simple programs, two very simple programs, to act as the client or attacker in our environment. The first is a very generic Modbus client program that accepts a function code and any other data and options. It uses PyModBus on the back end, and PyModBus is a very well supported Modbus Python library, which will handle all of the underlying networking for us. So for example, on the bottom left of this slide is a code snippet where C represents a Modbus TCP client object. And what we're trying to do is we're trying to read coils at a PLC. And so we take an index or address, the number of coils that we want to read, which is represented by N, and the unit number, which again is a device ID. Regardless of failure or success, we print our response, and in the event of a success, we obviously print the associated data. On the right here, we see example usage. So function 3, we want to read a register from the address of 1000, and as you can see, the PLC responds, or in this case, our VFD responds with illegal address. The second program is called CLICKPLICK, and this one leverages another Python library known as ClickPLC and takes advantage of ClickPLC's indirect addressing. Simply put, we can use a name or a tag instead of number now. And on the bottom left here, we can see some examples. So for control relays, for example, the symbol C, data registers, DS, for example, is a single word integer data register. Bottom right, you can see an example usage. So our target followed by a set request on the register of DS10, and we want to set the value to 6000. ClickPLC library utilizes asynchronous communications. This causes our program to be more modular, and as you can see the code sample here, simply to set PLC, we send the tag and values along with an IP. We establish connection, and we attempt to overwrite that value.
So finally, to deploy the actual lab for our POC, we used modules to define every aspect of the lab. The reason for this is that it allows us to have consistent and repeatable labs created by calling the modules. A module is created for deploying the ELK stack from scratch, security onion, and lab networks. These can get quite complicated, so it made sense to create a module that could simplify deployment. For example, this is the directory of our ELK module, which breaks up pieces by function. For the proof of concept, we kept things simple, with just the lab network module to create the network, a custom module defining VMs we needed for the POC, and the ELK stack module to test out collecting logs with Elasticsearch. Altogether, this made our main TF where we make the module calls look like this. You can see we're passing variables to tell the modules how we'd like things to be deployed and where. Once all this is done, we push the changed lab code to our GitHub repo on the production branch where it's deployed. Because of the large number of resources defined in the modules, the Terraform plan which shows what we're about to deploy is over 1,000 lines long, showing the creation of 27 resources. With a simple Terraform apply, we have the infrastructure required to run our proof of concept.
So this is the actual physical lab that we set up. In the blue box is the VFD, or variable frequency drive. This is exactly what it sounds like. It controls the frequency. In the pink box, we have the buttons that we set up. We made it very simple. We start and stop the motor, and we can change its direction and speed. The green box is the physical motor itself, or the actual motor, sorry. And the red box is the actual PLC. So for demo purposes, what we decided to do was turn the motor on and off remotely, change its direction, and then change its speed. Using the program that we introduced earlier, CLICKPLICK, that is essentially what we did. So we would set certain registers to be certain values, and these would be used to control the C addresses, which would be control bits, and the DS10 register, which is the speed of the motor. Finally, in this figure is the Wireshark packet capture, and you can see here the MODBUS packets being sent and returned. Not much to say about this particular figure, except that you notice the transaction IDs that we can use to track requests and replies, and obviously the function codes to see the actual operations that we requested.
Overall, the team was largely successful in accomplishing the project goals. The infrastructure was specified, a POC was developed, and an attack was simulated. The demo illustrated the ability to quickly spin up VMs and interact successfully and remotely with a PLC controlling a physical process. However, there were several lessons learned. Some were of a technical nature, other issues were related to the design and process. Given the huge scope of the project, issues came up with our ability to execute the vision within the finite time our group had. The final product felt rushed and cobbled together. Project creep proved to be a recurrent and impairing issue. Although great ideas were put forward, the sheer number contributed to attention drain. Using a cloud tech stack also created the issue of finding an individual who can handle the transition of the project from our team to future groups. The expertise needed is rare and be quite expensive. In the future, it will be advantageous to use a paid GitHub organization, as this allows for security features like branch protection, which prevents deploying, merging code unless it has passed defined checks or reviews. Currently, everything resides within a single GCP project. In the future, for ease of permission management, the project could be moved into a GCP organization, which will allow for several improvements to the setup. We intended on doing this, but were unable because of time constraints and a lack of need for our POC. It must be admitted that a higher budget would permit users to test additional PLCs, especially the ones that are used in real-world infrastructures and different architectures and ICS protocols. Furthermore, this project demonstrated only one protocol. With scalability and extensibility, the lab should be able to support as many protocols as needed.
That is our presentation. We want to thank you for your time and attention. And at this point, we welcome any questions or concerns or comments. Thank you very much.